Hi, my name is Becca Zombach. In this talk, I will be walking you through some of our work looking at geochemical heterogeneity in paleosols and how we can use resampling of profiles to think about how we can better constrain statistical uncertainties associated with paleoclimate proxies. So really, this work stems from the simple observation that anytime we go into the field to sample some geologic outcrop, there's always some limitation in terms of either spatial extent, lateral continuity, vertical availability. It's all dependent on the exposure. And when we think about what this means for paleosols and using them for paleoclimate reconstructions in particular, we have to think about questions like how spatially representative is this? If we can only sample 2 or 3 profiles from a limited outcrop, but we're trying to make basin-wide observations about climate or environment, how can we better improve that uncertainty? And so typically we end up sampling a very limited number of profiles, often close together, and that has big implications in terms of uncertainties around repeatability and reliability of these proxies that we're trying to use. And we're not the first ones to, think about this question. Other work has been done on the lateral and spatial variability of geochemistry in paleosols. So, for example, this is previous work out of our lab. In 2016, Hyland and Sheldon did a 1 kilometer transect looking at the geochemistry of some Eocene paleosols in the Green River Basin. And good news was that they found that geochemically it was relatively homogeneous, but they didn't really look into how to improve the uncertainty of the proxies that they were applying. And so in this work, we went over essentially to the next valley over and sampled a 3 kilometer transect through the same formation, the Eocene Wasatch Formation, and we sampled a laterally continuous, very well exposed paleosol. And in addition to looking at the geochemical heterogeneity of these paleosols, we actually did some statistical resampling of those profiles to try and constrain better what the uncertainty is in a paleoclimate proxy if you have 1 profile versus 3 profiles versus 10. And so that's pretty intuitive. If we take more samples, we should have a better understanding of how variable it is. And so in this transect, we took 11 profiles, although one, which is marked in the red star, actually ended up being at the next sort of paleosol couplet above ours. So within the continuous paleosol, we have 10 profiles, and then one that we actually compared to for a little bit of temporal variability of climate within the basin. So this was our field site. It was this beautiful exposure, great camping. And at the base of this system was a very large fluvial sandstone with beautiful crossbeds and big concretions that were then overlain by this classic fluvial paleosol deposit. And we were able to follow this great marker bed out for essentially the full 3 kilometers. And what we found across that distance in terms of sort of the sediment and physical appearance of the paleosols is that on the western side of the paleosols, at the start of our transect, we had sort of a classic brick red claystone paleosol. But then as we actually moved east, we saw that the paleosols started to become a little bit sandier, and they had a really dramatic change in color, which was, rather than being brick red, they started becoming very purple and sort of yellowish green, very mottled, which we interpret as essentially a shift in dominant redox conditions. Which in the context of this fluvial system and the spatial scales that we were working on seems reasonable. And they are pretty geochemically homogeneous, just as the previous work found, with one notable example, which is the calcium values. And we had a couple of discrete samples that are noted by these white and black sort of targets in the figure, where the rest of the profile had sort of low to average calcium values, and then these would have, 10, 20, 25% calcium. And this was interesting because we didn't see any obvious, calcium carbonate nodules or grain coatings. And so, one potential explanation for this would be some less obvious and more recalcitrant forms of calcium, calcium minerals, maybe coming from the winds. So this is actually a great demonstration of why it's so important to sample multiple profiles, because if you had happened to sample, only profiles 4 and 5, you might think, oh, wow, these have a ton of calcium. Whereas when you look at it in the broad sense, we see that it's actually sort of an irregularity. And so here we have the lateral extent mapped out by different horizons, so A, B, and C in blue, red, and black lines, respectively, with weathering intensity in the form of the chemical index of alteration on the y-axis. And what we see is there is some variability. The B horizon does tend to be more weathered than the C horizon, which is what we expect. And if we pull out that one overlying profile, we actually see that it fits in pretty well here, which just suggests that there's a period of relative climatic stability, in this little basin. And then looking at the ones where we actually had some of those high values, that's where we start to see some really big error bars, which are just the standard deviation. So those calcium values are really pulling down the CIA values for those profiles. If we then translate those results into our mean annual precipitation reconstruction, we see that they tend to be around the mean, which is this dashed line here. But there is this bimodal distribution where we have clusters right up here around the mean, and then some of these really low values that are, again, pulled by that calcium. And so this points to the importance of screening your samples and, again, just sampling multiple profiles so you can be sure to get a good, just sort of statistical understanding of the distribution of values in your paleosols. And if we compare R Valley to the next one over from the previous work, we see that they have pretty similar mean annual precipitation results, which is just a good verification that the proxy is robust at a slightly scaled up spatial extent. And then going into our resampling work, we used a Monte Carlo bootstrapping method and essentially just resampled the mean annual precipitation reconstruction with either 1 all the way up through 11 profiles being resampled. And then when we did that resampling, we also randomly nudged the precipitation value within the standard error associated with that proxy. And when we look at those results, we see essentially the pattern that we would expect, where if you're sampling just one profile, you have a very wide range of possible results. So this is a very poorly constrained reconstruction. And then as you increase the number of profiles that you're sampling all the way up to resampling all of them, you essentially converge onto a nice tight normal distribution where the range of mean annual precipitation along the x-axis here is essentially representing the standard error. And in terms of thinking about workflow and what you should do in the field, we actually see that somewhere in the middle between maybe like 4 and 6 profiles, you do start to see diminishing returns in terms of how much tighter your uncertainty gets versus how many more profiles you have to sample. We applied the same resampling to the site from the previous work and found essentially the same result, where as you increase the number of profiles, your distribution gets tighter, your uncertainty gets smaller, and then you also see the same sort of diminishing returns at a middling number of profiles. So what does this mean for, paleosol-based paleoclimate proxies? That's really what we're getting at. So we think it's good news. We, like the previous work, found pretty consistent geochemistry across paleosols, despite the apparent change in dominant redox conditions, so that's good. The similarity in mean annual precipitation reconstructions between the two sites, that's a good sign that the proxy is robust across, sort of tens of kilometer scale. And then in terms of our resampling efforts, we can recommend that you should screen your samples before you apply a proxy, which isn't news. You should try to sample multiple profiles when you can, which also isn't really news. The real implication here is just thinking about what is your question that you're trying to answer with these proxies. What level of precision do you need? because that will ultimately inform how many profiles you should be sampling to constrain the uncertainty to a level that's appropriate for your questions. And what I'm really getting at here is whether you are thinking about big general environmental shifts, so something like a transition between a forest and a desert, where you would have a really big, really obvious change in precipitation, as opposed to a nuanced or higher resolution climate record that you're looking at, where you'd expect a smaller magnitude of change, for example, 200 millimeters per year of precipitation, where you would need that lower uncertainty to differentiate between those results. So thanks for listening, and I look forward to taking your questions.